This is the second part of Chapter 12, and if you remember last week we learned about chi-square test, and this week we're going to learn about the t-test. So let's take a look at the t-test. So let's say, for example, we want to know if men earn more than women, or whether children at school A obtain higher state achievement test scores than students at school B. We could arrange the data in a contingency table and use this chi-square test. But by doing that, we would be changing the dependent information from interval, numerical data, to ordinal, which means we would be losing information. So we'd prefer to use an interval statistic, in this case the t-statistic, that can test hypotheses that two groups have different means. Each group is considered a sample, and this is called a two-sample t-test. And they can have an hypothesis in that they have the same mean, or they have different means, and then the same mean or different means, and in terms of different means, one group could be higher or lower than the other, and that's what we call a one-sided or a one-tailed t-test. We give some direction in that case. In just a different means, there's no direction, and it's called a two-tailed or a two-sided t-test. Now remember, we have variation in samples, and the degree of variation in the two samples affects the choice of the formula used to calculate the t-test. Variances of each population can be assumed to be equal or non-equal, and if the data for both groups come from the same subjects or cases, we could actually pair the data. The t-test can also test a single hypothesis. For example, if we want to test if the average salary of male teachers working in Pinellas County is more than $60,000, then our null would be that is equal to $60,000 versus the alternative, which is greater than. We would collect a random sample of male teacher salaries and determine if the mean is in fact greater than $60,000. All right, so let's take an example from your book, and they're looking at salaries of male planners versus the salary of female planners. And the research hypothesis, or H1, is that the average salary of the males is higher than the average salary of the females. And the null hypothesis is that they're the same, or perhaps the males are lower than the females. Research hypothesis in this case is one-tailed, and if the data show the average salary of female players is more than the male planners, we would not reject it. So in other words, we're cutting off an option here. If we use the two-tail, we would reject if there's a difference in salaries in either direction, but we couldn't make a conclusion about the direction. So the second thing we do is pick an alpha level, generally alpha of 0.5. Select a test statistic. In this case, we're going to use a one-tailed t because the research hypothesis states the males have a higher salary. And we're going to calculate the test statistic, and again, we'll generally use Minitab to do our calculations here. And then we're going to here's the formula for the test statistic, and this is assuming that the variances are equal, and the degrees of freedom are n1 plus n2 minus 2. And in our case, for this example, here's the data with the sample sizes and the means. And if we put those into the test statistic, we come up with a t of 4.28 and degrees of freedom of 533. Generally, you can say a t statistic, the absolute value of which is 2 or greater, is going to be statistically significant. And in this case, for alpha of 0.5 with 533 degrees of freedom, we would reject the null if the test statistic, the absolute value of it, exceeds 1.648, and in fact it does. So we reject the null and say that we have evidence to support that the average salary of male planners is higher than the average salary for female planners. And the normal distribution requires us to know something about the population variance when we want to test hypotheses about the mean. However, we generally don't know the variances, so we use the sample data to estimate it. So that's why we use a t-test rather than a normal distribution. As sample size increases, the t-scores approximate z-scores. So more on making decisions. So strategy: set the alpha level to reject the null, select the test statistic, compare the p-value that you get to the alpha level criterion, reject the null if the p-value is less than alpha, and there's a little acronym for you, mnemonic for you, help you remember, PLAR. So an example from your book, and this is actually interpreting chi-square data. So a probability sample of 830 citizens graded the city's police department. The investigators hypothesized the younger the citizen, the lower the grade he or she would give the police department. So the null is that age has no effect to the grades given, and we're going to use alpha of 0.5. And here's the Minitab output, and if you notice down the bottom here, it gives us the chi-square value, it gives us the p-value, and it gives us the degrees of freedom. And notice that there's one cell, it gives me a message here. One cell has an expected count less than 5, this cell right here. And our overall p-value is 0.008. And that one less than that where we have an expected value, we might want to think about combining either this way or this way, the columns or the rows, in order to eliminate that cell of having an expected value less than 5. So tests of statistical significance are used as part of the decision-making process and consider each statistical finding as part of the body of evidence that supports the truth or the error of a hypothesis. Particularly valuable in quality control, where a sample of, quote, products is used to inspect to locate systematic problems. So how do we report? We report the test statistic used and its value, along with the degrees of freedom and the associated p-value. Reporting the p-value allows the reader to make his or her own independent determination of whether that's significant. Reporting in the text, the researcher encloses the statistical results in parentheses. So the sentence would be, the average salary of male planners is higher than that of female planners, and then we see in parentheses the t-statistic, the degrees of freedom, and the p-value. If a contingency table is included, the information can be reported below the table. When several t-test results are reported, the mean standard deviations can be shown in the table along with the associated test statistic, and then footnotes can show the level of significance. And generally we'll have 1 asterisk, meaning the p-value was less than 0.5, 2 asterisks below 0.1, and 3 below 0.01. This can vary from journal to journal, but the more asterisks, the lower the p-value. And so here's an example from your book, and this was comparing the men and the women in the planning roles. So we've got men here, women here, and we've got all different characteristics. And then out here we've got t-statistics. Is there a difference in age? It appears that there is, and in this case they're using A, B, and C as footnotes on the significance level. And we were looking at the marital status, the race, the organizational characteristics, career attainment, income, and it looks like a lot of these are significant with the exception of the centralized management and the number of roles. So there are some alternatives to traditional statistics significance tests. The null can include a specific difference. For instance, we could say the average salary of the male planners is at least 20% higher. We can also use a confidence interval in place of reporting significance. The nice thing about this is it gives you a range of reasonable values for the mean. So if we look at the male and female planners, remember before we had a significant difference in the t-test, the confidence intervals show us that for males it's going from 31.49 up to 33.37. Notice the female confidence interval is below, it doesn't extend above the minimum for the male confidence interval, which supports our decision to reject the null. And also look at the salary income levels. Oh, this was age, I'm sorry, this is age and this is salaries here. We see the male planners on average are older than the females. And we see that male planners on average earn more than the females. Again, the confidence intervals don't overlap. Now, it would be interesting to do a regression model where we adjust for age or years of experience. So perhaps the females are making less because they haven't been working as long. And then report a degree of association. We'll discuss these in chapters 13 and 14 for correlation and regression. Replication is important. Sometimes we choose a different population or setting to see if we're able to generalize the results. So the male and female planners, maybe that was done in, I don't know, Chicago. Maybe we want to see if we can do it in Denver and get the same results. Remember that practical significance leads to further study, spurs policy decisions, or causes changes in behavior. And as a summary of what we covered in this chapter, we talked about test of significance. We talked about type 1 and type 2 errors. We talked about a t-test. We talked about a chi-square, and we had 4 steps for our test of significance. And then again, the p-value is the probability of a specific chi-square or t-value occurring if in fact the null hypothesis is true. Again, tests of statistical significance can be easily misinterpreted, and remember that practical significance should lead to further study. One significance test on its own is probably not going to lead to a policy change.